Welcome back everyone to yet another episode of Dave Does Math from Home. This is part 3 of our video series on section 5.5, Integration by Substitution. We've seen a bunch of hopefully pretty illustrative examples about how to do integration by substitution, even when the things don't match up quite right. There's a couple last things that I need to talk about. The first one, let's do an example. Let's say the integral of x to the 6th times the sine of x cubed dx. The inside is x cubed, the outside is the sine of x, and the other is x to the 6th and dx. So we can set w equal to x cubed. We can get dw is equal to 3x squared dx, and we can see if they match. This is an x to the 6th dx, this is 3x squared dx. The 3 we could handle. If the 3 here and not being a 3 here was the only difference between these things, that's a solvable problem. That this one is x squared and this is x to the 6th, that's not something that we can handle. That is not a problem we can solve. Coefficients are safe. We can add them in here and fractions on the outside, those balance each other, that's fine. Multiplication and division aren't safe. We can't take 4 of these x's to the outside and leave us with just 2 on the inside so that it matches. That's not something we can do. This problem is not solvable. With substitution. It's probably solvable with a different technique that we're going to learn much later, called integration by parts. But we're not going to worry about that right now. If you get a problem like this on the homework, where these things just don't match up and you can't make them match, then look for an option in the homework answers keys that say that you can't do it. If you get into this situation on a test or a quiz that I wrote, check your work. It probably means you made a mistake somewhere. Pretty much all the problems that I'm going to give you on integration by substitution are actually solvable by integration by substitution. Although there is something I want to say about the final exam and the tests you'll take much later in the semester. One of, overall, the most difficult parts of Calc 2 is by the end of the semester we're going to have a handful of different integration techniques that we can use to solve difficult integration problems. This is just one of them. Integration by substitution is one of them. We'll also, by the end of the semester, we'll also have integration by parts, integration by trig substitution. There's a couple others that involve weird trigonometric formulas or identities. We're going to have a handful of different techniques to use. And it can be difficult sometimes to distinguish when you should use one or when you should use the other. I usually describe this as the backwards chain rule because it involves composite functions, but I mean it also involves multiplication. So it's really easy to mistake this for sort of like a backwards product rule kind of a problem. And integration by parts is the actual backwards product rule, but those problems look like this. So one of the big challenges of succeeding in Calc 2 towards the end of the semester when you have all these is to learn to identify which problems require which solution techniques. And the good news is if you're doing a problem and you get something like this, that probably just means you're using the wrong technique and you should try a different technique. So don't be afraid to back up and start something else. Right now we only have the one technique, so if you get into the situation, it either means you screwed something up or the problem is one of those tricky homework problems that doesn't have a nice solution to it. But definitely be aware that there's going to be problems where the exact solution technique is not immediately obvious. So definitely keep that in mind. That was one thing I needed to talk about. The other thing I need to talk about in this part 3 of the section 5.5 video is what to do with definite integrals. So let's go back to one of our original examples. Let's talk about the sine to the 4th x times cosine x dx. Except this time, let's not do sine to the 4th, let's do sine cubed. This time I want to see what happens when we examine this from 0 to pi over 2. That's the plan. So you'll notice that all of the examples we've done so far have been indefinite integrals. I only wanted the antiderivatives, and the answers to all of them have involved that plus c that gets attached at the end. Now we're doing definite integrals, and there's two different ways to handle the definite integrals in this case. And the book always suggests one technique, and I don't like that technique. So this is another one of those times when the book and I will sort of disagree on things. As long as we're talking about that, the book also doesn't use the words inside, outside, and other, and it uses a different way to establish whether or not you can match the other with the dw. I don't even think it uses w, I think it uses u. So there's a lot of disagreement between the book and I in this section. So if you're doing the homework and using the homework's resources, like show me an example or help me solve this, and it's not matching with what I'm saying here, feel free to ask me about it, and then my cat just ran away. Feel free to ask me about it, and I will be very happy to sort out the translation between what I've explained here and how the book explains things. But let's look for now at the two ways to solve this. Both of these techniques are going to start the same. We're going to do the inside, outside, other. Inside is sine, outside is something cubed, other is cosine x dx. So we set w equal to the inside, which is sine x. We find dw, which is cosine x dx. These things match very nicely, so we don't have to worry about that. We can just do a straight substitution. And so now we have the integral. When we substitute this, sine cubed is going to become w cubed. Cosine x dx is going to become dw. This is the integral we're left with. And this is the part where sort of the two techniques diverge. According to the textbook, you should plug these x values into this substitution technique so you can find new values for w. So if we plugged in x equals 0 here, we would get that w is 0. And then w would be, that would be our new lower bound on this integral. And if we plugged in x equals pi over 2 here, we would get that w is 1. So we could evaluate this new integral in terms of w from 0 to 1. That's a thing that you can do. That works really well. I don't like that because I don't like that it creates such a sharp distinction in the steps you follow between definite and indefinite integrals in the middle of the problem. I prefer this process to go exactly the same for definite and indefinite integrals right up until the end, where you think at the very last step you're thinking, do I need to plug in some numbers, or do I need to attach a plus c and be done? So when I do these problems, I leave these bounds alone. I'll keep this x equals 0 and x equals pi over 2. I will introduce this x equals bit because this is a reminder to me that I shouldn't just plug these values in for w, because these are not w values, these are x values. but I leave them alone as originally written. I don't mess with those. I do the integral as normal. This will be w to the fourth times 1/4. I don't need to add a plus c. I do need to evaluate at x equals 0 and x equals pi over 2. But again, I'm not going to plug these x values in for w. First I'm going to unsubstitute this w back into a sine. Sine to the fourth x from 0 to pi over 2. If you do it this way, all of these steps so far match perfectly with all of the steps for doing an indefinite integral. All of the other times we've done this without bounds, these are the exact same steps we follow. You identify what's what, you set w equal to the inside, you find dw, you see if they match, you can make them match if the difference is a coefficient, you substitute, you integrate, you unsubstitute. Those are the steps in order. And now that we're at the very end, instead of adding a plus c, I can plug in these numbers back into the original. If you do it in the book's technique, you have to interrupt those steps halfway through to find new bounds, and then you plug those new bounds into this without ever unsubstituting, and that just feels like a weird departure from the rest of the technique. So I prefer it this way. You, of course, can use whatever technique you think is easiest or best or makes the most sense. I'm not going to be prescriptive about this. You can, it's up to you. Be the master of your own destiny. Do whichever technique you like best. I just wanted to show you both. In my technique, I'll plug pi over 2 into sine of x and get 1. So this will be 1/4 of 1 to the fourth minus plugging 0 into this would give me 1/4 of 0 to the fourth, which is exactly what you would get right here if you plugged in 0 and 1 for your w values. So it's the same thing. It's just when you're plugging your x's into your inside function. And this will give me 1/4. That's all I have to say about section 5.5. This has been a chunk of videos. I think we're pretty swiftly approaching the 50-minute mark of me just non-stop talking about integration by substitution. So I hope that it was understandable. I hope that the homework goes smoothly, and if not, you know where to find me.